There is a claim circulating that suggests the iPhone 17 Pro managed to run a 400 billion parameter model. This number alone is staggering. To put it in perspective, that is roughly 100 times larger than the models most people interact with on a daily basis. The idea of fitting that much intelligence into a pocket-sized device challenges everything we know about how silicon works. If this were true, it would represent a massive leap forward in edge computing. However, to understand what this actually means, we have to look past the headlines and examine the raw physics of the hardware. We are talking about memory bandwidth, thermal dissipation, and power delivery. These are the three pillars that determine whether a machine can think or if it simply overheats and shuts down. Let us start with memory. A model with 400 billion parameters is essentially a massive library of knowledge encoded in numbers. Each parameter requires storage space. In a data center, you have racks of servers with hundreds of gigabytes of memory available. You have the luxury of space and cooling. On a mobile device, the memory is measured in gigabytes. This creates an immediate conflict. The hardware simply does not have the raw capacity to hold the full precision of the model at once. The only way this becomes feasible is through extreme quantization. This is the process of compressing the numbers. Instead of storing every value with high precision, the system reduces the data to lower bit depths. This allows the model to fit into the available RAM, but it comes at a cost to accuracy. It is like trying to fit a high-definition movie into a standard-definition stream. You can make it work, but the quality suffers. The engineering challenge here is not just fitting the data, but moving it fast enough to be useful. This brings us to the second constraint, which is memory bandwidth. Even if you can fit the compressed model into the chip, the processor needs to read that data constantly to generate responses. Think of the memory bandwidth as the width of a highway. A 400 billion parameter model is like a massive convoy of trucks. If the highway is narrow, the trucks have to wait in line. On a mobile device, the memory bus is not as wide as it is in a server. This means the processor spends a significant amount of time waiting for data to arrive. The neural engine inside the phone is designed to speed up specific tasks, but it still has physical limits. When the system is pushed to run such a massive model, the bottleneck becomes the speed at which information can travel between the processor and the memory. If the data cannot move fast enough, the user experience degrades into a slow, lagging stream of text. Now consider the heat. This is often the most immediate physical barrier. Running a large model requires the processor to work at high utilization for extended periods. This generates significant heat. In a desktop computer, you have large fans and heat sinks to push that heat away. In a phone, the space is extremely limited. There is very little room for airflow. The device relies on passive cooling and conductive materials to spread the heat. When a chip generates more heat than it can dissipate, it begins to throttle. This means the processor intentionally slows itself down to prevent damage. For a 400 billion parameter model, the heat generation would likely exceed what the thermal design can handle for more than a few minutes. The result is a burst of activity followed by a slowdown. This limits the model to short tasks rather than long, continuous conversations. It is the difference between sprinting a race and running a marathon. The phone can sprint, but it cannot sustain that pace indefinitely. Power consumption is the third critical factor. A 400 billion parameter model is computationally expensive. It requires a high voltage and a sustained current draw to perform the calculations. Mobile batteries are designed for efficiency, not peak performance. They are optimized to last all day on typical tasks like browsing or streaming video. When you ask the device to run a massive AI model, the power draw spikes dramatically. This puts stress on the battery chemistry and the power delivery system. If the device draws more power than the battery can safely supply, the voltage drops. This can cause the system to become unstable or shut down unexpectedly. Even if the battery can supply the power, the heat generated by the electrical resistance will compound the thermal throttling issue. You are essentially fighting a battle on two fronts. The battery wants to run out, and the chip wants to overheat. The feasibility of this feat signals an impending trend where agentic AI capabilities, previously exclusive to data centers, will migrate to edge devices. But this migration is not without its costs. Success in this scenario likely depends on a hybrid approach combining model distillation, sparse activation techniques, and hardware-software co-design. This means the software must be smarter about what it asks the hardware to do. It might only activate a small portion of the model for a specific task. It is like using a specific tool from a toolbox, rather than bringing the whole toolbox to the job site. This reduces the load on the memory and the processor. It suggests that raw model size alone is no longer the sole determinant of on-device viability. The efficiency of the implementation matters more than the number of parameters. There is a significant gap in the documentation linking this specific device to such a massive model execution. The consensus across available technical analysis suggests that the claim is likely misinformation or a conflation of separate technological advancements. No factual basis exists in the provided data to support the user's query regarding a specific demonstration. This does not mean the technology is impossible, but it does mean the current reality is different from the hype. The primary knowledge gap is the lack of any credible documentation linking the iPhone 17 Pro to such a massive model execution. We must remain skeptical of claims that ignore the fundamental laws of physics. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.